The Autonomous Operating System, the AOS, model-based plug-and-play autonomy for robots in partially observable probabilistic domains with noisy sensing, a research of Or Wertheim and Dan Suissa under the supervision of Professor Ronen Brafman. Motivation. An increasingly wide range of robot skills is currently available. How can an autonomous robot use them to perform tasks? The current state of the art is to use handwritten scripts or state machines to schedule skills into effective behaviors. The challenge is that scripts or state machines are non-optimal, hard to maintain upon environment change or robot skill upgrade. The solution is to use AI planning algorithms to control the robot. The problem is it requires AI expert and a significant integration effort. Our goal is to provide plug-and-play task-level autonomy for robotics. Our solution, the Autonomous Operating System, the AOS, which offers several advantages. Conceptually, we provide full POMDP support with stochastic actions, partial information, noisy sensing, complex goal, and optimized behavior while balancing trade-offs. We offer an abstraction mapping, which is an explicit and principal mapping between the skill model and skill code. We use generative POMDP models that are based on probabilistic programming language constructs. It offers greater expressive power, easier to specify, and enables much faster sampling rates. Generically, we provide a true plug-and-play system. Even properly documented skill code, no additional programming effort is needed. Documented skills can be added incrementally and used by the system. The AOS uses reinforcement learning to auto-generate MDP heuristics of POMDP solvers. The system has a GUI to visualize the robot belief state distribution and understand the robot's behavior. So how do we use the AOS to develop an autonomous robot? The first step is implementing basic robot skills like navigation, object detection, or arm manipulation. This is out of the system scope. The next step is documenting the skills and environment. An environment file specifies skill-independent aspects of the model. These include state variables, terminal states, initial belief, and state-dependent rewards. Each skill is documented using an SD and an EM file. The SD file describes the expected high-level impact of applying the skill, how state variable value change, the skill-associated reward or cost, and the information the skill will supply. Semantically, these are the POMDP's transition, reward, and observation models. The AM file connects the more abstract model of the skill with the skill code. It specifies how to activate the skill code and how to generate from it the model level observation. We now show some of the AOS-based systems we implemented. Our first system is a tic-tac-toe playing robot based on a Panda robotic arm. It uses two skills, drawing a circle in a cell and detecting the board state. Our goal was to test the system's plug-and-play capabilities and how easily it can be modified to address environment and task changes. On the left, we see the robot playing a regular tic-tac-toe game. Simple skill documentation and an environment file suffice to make it work out of the box. In the middle, the arm is faulty and succeeds marking the center cell only 50% of the time. If it fails, the turn passes to the human. Optimal behavior is now very different. A script would need complete rewriting. In the AOS, we just slightly changed the draw skill SD file to capture this stochastic effect. On the right, the game was changed. Marking cells adjacent to marked corner cells reward a player with a point. Manually rewriting a script to win such a game is non-trivial. In the AOS, we only need to change the EF file reward model. Next, we see a simulated armadillo robot, a mobile base with an arm, with partial information, noisy sensors, and stochastic actions. The environment includes a room with two tables, each with a can on it, and a corridor with a person. One can is difficult to pick. It is on the table adjacent to the robot. The robot's goal is to give a can to the person. We implemented three skills: pick can, navigate to a person or a table, and serve a can to the person. On the left, we see the behavior of a rough model. It assumes identical probability of a successful pick for both cans, so the robot goes for the harder can which is closer. Pick returns a noisy success observation and solve provide no feedback, so after it first serve attempt, the robot returns to the table and tries to repeat the process. In the center, we added an observation skill that more accurately reports whether the arm is holding the can. Now the robot verifies pick success. Only if the result is positive does it serve the can and stops. On the right video, we see a finer pick model in which success probability is conditioned on the robot's position. Here, the robot first moves to the other table, where pick is more likely to succeed. We see that the AOS is sensitive to different model properties. Such sensitivity is only possible with a rich decision model like a POMDP. Finally, we see the toy collection domain. On the left, we see a Turtlebot gazebo simulation in which a robot receives a reward for bringing toys to a child. Toy locations and values are unknown to the robot. The robot's navigation skill may fail and has noisy reports for its success. Its pick skill can only be used 6 times. It works only when the robot is near the exact toy it tried to pick, and returns an accurate observation of its success. On the right, we see the AOS belief state visualization GUI. It uses graphs to visualize the belief state distribution over each variable. It can also generate image for better visualization. Here we see a table in which rows correspond to toys and the robot, and columns correspond to location and possible toy values. Greater color intensity corresponds to higher probability. With the help of the visualization tool, we can see how applying a probabilistic navigation action adds uncertainty, and how observations such as successful pick influence the uncertainty. Such fine-grained modeling of the robot's state of information and derived behavior is only possible when using POMDPs. Let's zoom in and see how the AOS trade off risks and chances, which is only possible when using POMDPs. The blue toy has an expected higher value, yet it is likely to be at location 0, where the navigation skill is expected to fail and the observation is less accurate. Navigating to location 3 has better success rates and more accurate observations, yet the red or black toys are likely to be there and have a lower expected value. So the robot prefers to navigate to location 3, tries to pick the valuable blue toy, which fails, updates its belief, and succeeds in picking the red toy. Notice that the robot location becomes certain only after a successful pick observation. This is the power of POMDPs. Thank you for listening.